So just to develop this, let's do a calculation for the power output of a Saturn V rocket. Now the Saturn V rocket was the rocket that launched humans to the moon. And when we look at a Saturn V rocket, the first thing we want to do is break it down into a modeled system. That is, we want to take the physical entity of this rocket leaving the launch pad, and we want to think about what actually occurs inside, and we want to simplify the structure of that physical rocket into a modeled system. So when we do that, the first thing we're going to do is add kerosene fuel to oxygen. And there are pieces of ice falling off of that rocket as it lifts off the launch pad. And that's because we're actually using liquid oxygen and combining that with kerosene. Now kerosene is similar to gasoline, except it's a longer molecule. It's C12H26. That's the kerosene that's burned in the Saturn V rocket. It's also the fuel that fuels all of the aircraft that you ride on. And you can smell this kerosene in airports because when engines start, they tend to exhaust a lot of unburned kerosene, and so it's the typical odor around an airport. But we want to mix it with oxygen, releasing that chemical energy, and that product is CO2 and water. But we need to balance that equation to do the calculation. So to balance it, we need 2 molecules of kerosene, we need 37 molecules of oxygen, and that produces 24 molecules of CO2 and 26 molecules of water. Now, the fuel volume in a Saturn V rocket is the important quantity here, because if we have the fuel volume, we've just calculated the fact that that fuel produces 10 kilowatt hours of energy per liter. It turns out that the fuel volume of the Saturn V rocket is 8.5 times 10 to the 5 liters. That's an interesting number. It turns out that that's about the volume of the fuel tanks in an aircraft that you would ride from New York to Beijing. And so this is a reason that you want to make sure the aircraft takes off, because this is a lot of energy, as we'll see. So let's calculate the energy content of that fuel. That is equal to the volume, 8.5 times 10 to the 5 liters. But now we can multiply that immediately by the energy content per liter. That's 10 kilowatt hours per liter. And that gives us energy content of the fuel of 8.5 times 10 to the 6 kilowatt hours of energy. All right, when we convert that back down to joules, that gives us a total of 3.1 times 10 to the 13 joules. That's a lot of energy. But the question we asked was, what's the power output of the Saturn V rocket? And there are 2 aspects of this. One is the energy consumed per unit time calculated based on the chemical energy, and the other aspect is the actual power output. And to determine the actual power output, we have to calculate the rate at which chemical energy is being converted, and we have to multiply that by the efficiency of a rocket engine. Now, as we will see in calculating the efficiency of an automobile, we only get about 15% of the chemical energy into motive force from an automobile. They're extremely inefficient intrinsically. But a rocket that burns kerosene and oxygen directly actually has an efficiency of 60%. So when we calculate the power that's delivered by that Saturn V, that's going to be the efficiency multiplied by the change in energy per unit time, which is to say the chemical energy released per unit time. So I have 0.6, that's my efficiency, and then I take the amount of energy contained in the burning of that kerosene. That's 3.1 times 10 to the 13 joules. And now I divide it by the burn time of that Saturn V rocket. And the Saturn V rocket burns through 3 times 10 to the 13 joules of chemical energy in 170 seconds. And when I calculate that out, that turns out to be 1.1 times 10 to the 8 kilowatts. And I also know that 1 kilowatt is equal to 1.3 horsepower, and that gives me 1.5 times 10 to the 8 horsepower as the power output of that Saturn V rocket. That's 150 million horsepower produced by that Saturn V rocket. And if you calculate the fraction of the total consumption of energy globally during that 170 seconds, it's almost 1%.